I actually had a question about the activities that we're doing as like homework. The exercises that you're talking about, the ones that are in the book, are you talking about the where it says think about it objective? Because I know when I was like reading those and trying to do those, they weren't really like, some of them weren't really questions.
No, they're at the back of the chapter.
Okay, perfect. That's what I thought. I wasn't sure exactly.
Yeah, you're not. Yeah, that's been confusing for everybody. One reason I tried to say read through the whole chapter, and you'll see the exercises, the activities at the back, or exercises at the back. That's a good question. I didn't think that would be, well, you know, you're reading through it, you see that, you think, okay, I have to answer that. I totally get it. Anybody else? No? Okay. Okay, well, let's see. Okay. All right, so I'm going to share my screen. Can you see the PowerPoint?
Yes.
Awesome, cool. Dr. Takis gave me a thumbs up because he's been having that problem too. Okay, so we're going to look at sedimentary rocks in lab on Wednesday as well. It's going to be a little bit easier than the minerals. The minerals lab is probably the hardest one, but you'll see the more common minerals in these rocks. So, wait a minute, we did this one already. I'm sorry. I'm thinking of lab. Okay. Woohoo. Sorry about that. Igneous rocks, that's what we're doing next. It's been a day. It's been a really, really day. There we go. Well, either way, we're still going to look at sedimentary rocks in lab. All right, there we go. Has anybody seen Welcome Back, Kotter at all? I keep wanting to do, yes, Professor Takis, we want to see sedimentary rocks again. Sorry. He would do that to the guys. Mr. Kotter, da da da. Well, da da da. Anyway, it's funny if you ever want to. You ever want to see that? It's silly. Okay. Okay, can you all see that?
Yes,
chapter 4, cool. Thank you for telling me that. And if it doesn't, if you can't see this, the slides move forward, please shout out and let me know. Okay, usually we'll have another chapter on volcanoes, but we're going to kind of combine them in with igneous rocks because they are definitely connected. So igneous rocks form when magma, which is the melted rock inside the crust, cools, crystallizes into rock. Magma is formed by what's called partial melting inside the crust. When magma erupts out of the crust, say through a volcano, then it's called lava. So lava is on the surface and magma is still inside the crust. And eruptions can be of varying degrees of explosive gradation down to very goopy Hawaii type eruptions. So magma contains three components: a liquid portion, which is called the melt, some crystals, some solid silicate minerals floating around, and most important, dissolved gases, which are called volatiles. I kind of think of, if you think of magma as kind of like oatmeal, you've got the oatmeal grains in there, then you've got the liquid, and then the vapor, the water vapor steam coming off your oatmeal. So the dissolved gases are literally dissolved in the magma. If you've got a can of pop or a bottle of pop next to you, when you open that pop, you hear the ksh and the bubbles start coming out. That's dissolved carbon dioxide in the sugar water, or diet sugar water, whatever you've got in your pop. So to give soda that fizzy bite, they dissolve carbon dioxide in the liquid. Same exact thing. We've got gases, mostly water vapor. Carbon dioxide would be the second most common, and then sulfur dioxide, which is the rotten egg smell. So those are the most common volatiles that come out of volcanoes or any type of eruption. And once the magma breaks the surface, that's when the volatiles come out of solution and escape. So just like when you're opening your bottle of pop. So magma crystallizes in kind of certain ways, specific ways. So here's where a rock like a granite starts to form. The silicon and oxygen atoms start to link together and bond to form those tetrahedra we talked about before. Then as the magma body starts to cool, those tetrahedra start to join, and that's how minerals begin to crystallize. The minerals that have plenty of space will grow into larger pieces and have well-developed crystal faces. So those quartz that you saw, the long pieces of quartz with the pointy tip, those are more well-developed crystal faces. So they had a little more space to grow that large in that way. So here's granite. Granite's my favorite rock. I lived in New Hampshire when I was a kid, and so that's why. So we've got different minerals. Granite cools inside the crust. This is magma that is not erupted out. It's underneath the volcano in what would have been an old magma chamber. So the pinkish minerals are the orthoclase or potassium feldspar. The black are the amphibole hornblende, the hornblende that you saw, maybe the pyroxene, but think about the hornblende. The clearish is going to be quartz, and the whitish gray is plagioclase feldspar. Okay. And you'll notice there are more light colored minerals than dark colored minerals in granite. So something like granite, when it crystallizes what's called at depth, inside the crust, that's called an intrusive igneous rock. So it crystallizes in the crust. There's your mnemonic device there. The way we see them is by later on erosion takes off the surface material or sedimentary rocks or whatever happened to form on top, and then the granite's exposed at the surface. Or by, we see a little bit and then we start drilling and mining and pulling it all apart. But usually, for the most part, erosion pulls all the surface things off. When lava is ejected from a volcano, then that's an extrusive igneous rock, so it exits the volcano, it's on the outside. So here's another diagram. On the left, you've got your starting point of magma in a magma chamber, and there's a volcano. And then when the volcano becomes dormant, maybe that magma starts to crystallize right where it was. It can move back down into the earth. Maybe there's another magma chamber beneath it. So you get all kinds of different things, but this is the simplest way to show it. And then you've got the extrusive rocks that have been ejected, like the lava, like basalt from Hawaii that's flown over the surface. So igneous rocks are composed of silicate minerals. We've got the dark colored silicates, olivine, pyroxene, amphibole, biotite. Those are the ones you're probably going to see more. And then the light colored silicates, quartz, muscovite, and the feldspars. Those are the ones you're probably going to see more as well. Don't let this scare you. There's a range of compositions of the different minerals in igneous rocks. So when you're going to identify an igneous rock, you hold it in your hand, you look at it. A granite will always have that pink feldspar in it. Okay, so we've got a good percentage of that. A granitic rock can have this kind of a range. Granitic is also called felsic. And you're going to have muscovite, the clear mica, and quartz in there, and then plagioclase and a few dark colored minerals. Magma, igneous rock, can also be an intermediate composition. So there's no potassium feldspar, I know what this shows, but there's really, for your purposes, there's no pink crystals. It's going to be light colored and dark colored. We have one, the diorite. Everyone calls it the Oreo cookie rock because it looks like crumbled up Oreo cookies. It's black and white crystals. Then you can have a composition that's called basaltic or mafic. These are going to be mostly dark colored minerals. The rock's going to be dark green or dark black. Okay, you won't really see any light colored minerals in there. And this is basalt, Hawaii. Right, Hawaii has black rock, black sand beaches. It's all basalt. Deeper in the crust, that we don't see this at the surface because it's this kind of rock does not come to the surface, but we've deduced from looking at rocks and looking at what we'll talk about, seismic, earthquake measurements, we've deduced that inside the mantle we've got what's called ultramafic, which is a peridotite, not peridot, but peridotite. So it's mostly olivine, mostly pyroxene. It has, yeah, okay, it's got a few light colored, but it's got the least amount of light colored minerals. So the thing to keep in your mind is that granitic has the most silica or quartz, SiO2, and you get less and less quartz the darker you get. This is probably this is the reason why they separate like this. Granitic rocks melt at a much lower temperature. Ultramafic rocks or basaltic rocks melt at a higher temperature. So the light colored minerals will melt at a lower temperature. That also means they crystallize at a lower temperature. Okay. Yes. So basaltic rocks will crystallize at a higher temperature. Okay. That's the main thing is this is how you identify them. Look at the different colors of minerals, what you might have. Also, you might have a coarse grained or large grained texture, which the granite, as you saw. Then you might have a fine grained texture. You probably won't be able to see those crystals. They're small. So felsic is shorthand for feldspar and silica because of the composition. Granite is the most abundant rock in continental crust. Mafic or basaltic, no quartz, and at least 45% dark colored silicates. It turns the rock black or very dark green. That's what it's going to look like. And mafic is shorthand for magnesium and iron. They are higher density, they weigh more, they're heavier, and the ocean floor and lots of volcanic islands are made up of basalt rocks. You can also see, if you see basalt in the middle of a continent, that had to have been from some kind of lava flow from a volcano millions, billions of years ago that erupted just basalt. All right. Any questions so far? That whole composition chart, you'll have that in lab. You'll have a little simpler version of that in lab. All right. So on the left there is a granite. And the bottom photos are from a polarizing microscope. So this is a thin section. They take the rock, and I've actually done this. This is pretty cool. You glue it to a glass slide, and then you cut off with a diamond saw most of it, and then you polish it so that you can just get light through it. That's what this looks like under microscope. So this bright white is quartz. Here's your feldspar. Remember the striations on feldspar? Here's how you see that under the microscope. So you can identify minerals by what they look like under the microscope. So coarse grained means it's got large enough grains or crystals that you can see. Told you they don't like thunderstorms. And then on the right, you've got a basalt. It's hard to kind of see. This looks like more of a grayish, but basalt is usually going to be that black. And again, under the microscope, fine grained texture, very, very small crystals, mostly dark colored silicates, the pyroxene. Okay. Intermediate is just going to be the black and white or light gray crystals. And intermediate is also called andesitic because most of this rock that we've seen comes from the Andes Mountains. The Andes Mountains produces a lot of this composition. So the Andes are along the ocean margin of South America. So that's the seaward margin of the continent. And then ultramafic, rare on the surface, but olivine and pyroxene. If you, let's see, continental crustal rocks have a lot of silica in them. Then also the basaltic rocks have, 40% about silica. So that's still a lot. If you can measure the amount of silica, then you can make a very educated guess about what the magma composition was. Also, the amount of silica in the magma contributes to how that eruption might occur. So if a granite or granitic magma does erupt, then it will erupt at a lower temperature and it will be very viscous, very thick. Viscous is a term for how well does something flow. So the higher the viscosity, the less it wants to flow. So honey is more viscous than water. Basalt magmas have lower silica, so they are more fluid and they erupt. They're a higher temperature when they erupt. So when an andesitic eruption occurs in the Andes, it's going to be more viscous. In Hawaii, you've seen all the photos and stuff online. So it flows really, really quickly, really smoothly. All right, texture. Again, texture is the size, the shape, how the crystals, how they are arranged, how they are connected and bonded together. The texture will tell you a lot about the magma it came from and about how it was either erupted out or cooled, if it's intrusive or extrusive. So the slower a rock cools, you'll get larger crystals because it's giving them time to grow larger. The faster the rock cools, you'll have smaller crystals. They don't have the time to grow. The amount of silica will also influence the type of minerals, and the amount of volatiles will also influence the texture. All right, so you're going to see all of these in lab. Obsidian is up there on the upper left. It's glass. It has been thrown out of the volcano, though it's lava, and it quenches immediately. So it's gone from 2,000 degrees to essentially 0, 70-ish degrees at the surface. So fast, it doesn't have time to crystallize at all. It's natural glass. On the upper right, we've got pumice. It's the same thing you might buy in the store for rough skin. All those holes in it are from escaping volatiles. This rock, again, cools so quickly that it doesn't form real crystals, but all those bubble structures are still left behind. And that's called vesicular texture, vesicles. Left middle, porphyritic. I'll show you a piece, but I'm not going to ask you to identify one. Bottom left, that's granite, and it's coarse grained. You can see the crystals and minerals. So that's an intrusive rock. The obsidian and pumice are extrusive rocks. Right middle, pyroclastic. This is all kinds of stuff. It's ash, it's rock of any size from a very explosive eruption. Think Yellowstone. If you've ever been there, if you haven't, definitely go. It's really cool. If you've ever been there, you've seen the walls of feet thick of this kind of stuff. And then the bottom right, that's a basalt, and it's very fine grained. You can't barely, or maybe if you can, very barely see the crystals. Probably won't be able to see them. I know I talked before the slide comes. I like the photos and the drawings. I think it helps you see things better. One thing a blob of magma or magma body might do is move through the crust from somewhere at depth, and maybe it erupts at one point before the rest of it crystallizes. That's one reason why we get such different mineral compositions. You know, why isn't everything basalt that erupts? Part of it crystallizes out, leaving those lighter colored silicate minerals. So then that can cool and crystallize later or somewhere else, and that forms granite. So fine-grained, rapid cooling, microscopic crystals, coarse-grained, slow cooling, larger crystals, and porphyritic is kind of explosive mix of all kinds of stuff. So here's a porphyritic rock just to show you. So it's large things in smaller microscopic crystals. Vesicular just like the pumice, voids, bubble structures left behind as the rock cools. So this is an extrusive rock. Obsidian, again, so cooled so quickly it's essentially quenched, turned into glass. Pyroclastic, very explosive. Think Pompeii. All of that eruption that happened there, that was a pyroclastic eruption. Pegmatite, I'm not going to ask you to remember that. Very coarse-grained, more coarse-grained than the phaneritic. We've got a pegmatite, I think. No, I've just got porphyritic. But all right. So here's Hawaii. This rock here is basalt, and yeah, it's got a vesicular texture because of the slow eruption, and the gases escaped quickly, and it just cools very quickly as it comes to the surface, as you can see. So you wouldn't want to step on that because you could break through that thin crust and get into that lava there. All right, so igneous rocks are identified based on the texture and the mineral composition. So the magma is what gives the rock its chemical composition, and then the texture is from, does it cool quickly or slowly? So we can have rocks with different textures, but same composition. And this is very similar to one of the other diagrams there, but this just shows you the rock, so this is probably a little easier to read. So the left column, granitic rocks, are going to be granite, which although it's got large crystals and it's intrusive. Rhyolite is the extrusive version, same composition. You can call obsidian and pumice granitic as well. They've just crystallized so quickly you can't see those other minerals just looking at a piece in your hand. But yeah, and then intermediate or andesitic composition, that top one is diorite, coarse-grained, andesite, fine-grained, and then you can have a porphyry. Basaltic or mafic, the coarse-grained version is called gabbro, and it's black and green. Basalt is fine-grained. And then you've got scoria down there. I guess because it's dark, you can call it a basaltic rock. And I've got a piece of welded tuff to show you, pyroclastic rock in lab. All right, so we've got a lot of granite in the crusts. We all have seen it on countertops and stuff like that. Rhyolite is the fine-grained equivalent. It's got that pink color because of the feldspars in it, and it is less common. Obsidian, dark-colored, usually glassy, but it's got the same composition as granite. The dark color is from some iron and magnesium ions that just didn't quite form dark silicate minerals. And pumice, again, usually you find it with obsidian. They're both extruded quickly from a volcano. Here it says, will float when placed in water. Well, the sample we have in lab doesn't float. I tried it. Hopefully, I don't know, maybe we'll find a piece that does float in water, like this one. So the one we have in lab made me a liar. So try it. Andesite is the fine-grained intermediate composition. It looks gray. Diorite is the coarse-grained, so that's intrusive, and it's got black and white crystals, or maybe some gray in there, but it looks like an Oreo cookie. So andesite is an extrusive rock. And basalt, mostly pyroxene, some feldspar, you won't be able to see it though. Maybe some olivine in there. This is the most common extrusive igneous rock. It makes up the ocean floor, the igneous rock beneath any sediments on every ocean floor. Iceland. Usually I show a video about Iceland volcanoes, and that island is just totally all basalt. Hawaii, same thing. Gabbro is the intrusive equivalent, same composition, and again, mostly pyroxene and olivine. And we find gabbro beneath the basalt in the ocean crust. So it's underneath whatever layers of basalt might be on the top part. Welded tough and tough. This is the ash with other different size rocks all blended together. This rock, it's so hot when it's ejected, just like obsidian pumice, that as it's flying through the air, it will start to coagulate. Then when it lands, I don't know anyone in Minnesota, then when it lands and starts to form layers, it's still hot and it starts to crystallize together and form those layers of rock. Fuse together, that's the word. So Yellowstone, pretty much. Here is oh heck, that's not Yellowstone, I don't think. Now I have to look this up. But that is a very, very tall cliff of welded tuff. So whatever erupted that was a huge eruption. Maybe there were two, because you've got this kind of a bedding plane here. So maybe there were at least two in this picture. Okay, magma. The mantle is also solid, just like the crust. You may not realize it is. It's just so hot. It doesn't quite melt. It's really, really hot, but it hasn't quite melted yet. And that's because it's all under pressure under the crust. So the magma, the earth is really cool. The mantle material is flowing from the surface down towards the core and then back up to the surface in different compartments all around the planet, which we'll look at later. So as that mantle material, magma, moves towards the surface, it comes to places where we've got two plate boundaries. So think the mid-ocean ridge. That's what's helping to generate the ocean crust at the mid-ocean ridge, and it kind of pushes the two continents, North America and Europe, well, however you can see me, one on one side and one on the other side. That's where most of magma is produced. And we'll talk about subduction zones. We get some magma produced there. Also, when a rock is buried by a tectonic process and heated enough and melts, then that generates magma. Okay, why is there so hot? Well, it is because it's all that hot rock is, again, contained in the crust. If your grandparents or great-grandparents ever had a pressure cooker and you're boiling, as my grandmother did, boiling some cabbage to tasteless mush. So you're boiling something in water in that pot and pressure cooker. So that water is boiling, but it doesn't turn to steam because it's still contained in the pot. Now a little bit comes out that little doohickey at the top, but most of it hasn't quite turned to steam. That's like the mantle. It's just hot enough before it can melt. And that's because of all the pressure keeping it inside the crust. So because of that, we've got what's called the geothermal gradient. This is where we get good geothermal energy out of, because as you go deeper towards the core, at least through the crust. As you go deeper, you get warmer. The rocks get warmer. So in the upper crust, 10 miles, then as you go deeper, every kilometer, the temperature increases by 25 degrees Celsius. When the rock in the lower crust and upper mantle, that ultramafic rock, when the that pressure is released a little bit, the melting point reduces and that material will melt and come to the surface and form, let's say, the mid-ocean ridge. It's more buoyant, comes up to the surface. So that moves the tectonic plates around as part of it. So you have to have that decrease in the pressure, water being added from the ocean, it percolates through fractures, and the temperatures increased because of the release of pressure. This is called decompression melting because you're releasing the pressure. So then the melting can occur at a lower temperature at the surface and a higher temperature the deeper you go. So if a mineral isn't going to melt at a certain temperature, at a very hot temperature, then it won't. But if it moves towards the surface and the temperature gets lower, then it'll start to melt. I know this is probably confusing. I apologize. Just think about the pressure cooker. So when you've got the mid-ocean ridge pulling apart, that magma comes up, the pressure is released, it melts completely. And that's really, you're reducing the pressure. So this occurs at diverging plate boundaries and also hot spots like Hawaii. And that magma is called a mantle plume. It's coming straight up from the bottom of the, inside the mantle, a lot deeper. Okay, here's the picture. So decompression melting, once the magma comes to a certain depth or moves up towards the surface, the pressure gets released. It buoys up into a magma chamber and starts coming towards the surface and pushes those two plates apart. If you add water, then this causes the magma or rock to melt at lower temperatures. So this increases the fact that the rock will melt as it gets near the surface. This usually mostly occurs where you've got a subduction zone. So the Andes Mountains, perfect example. You've got South America and you've got the Pacific Plate. I do this a lot in class. Subducting under the Andes Mountains. As this plate moves under, it's taking water with it, and that dissolves into the magma. So then the fluids migrate into the magma and begin to lower the temperature, and that triggers what's called partial melting, and that's where only the low temperature minerals will start to melt. You can also have the magma chambers or magma bodies. As they move up, they don't just exactly sit there, they're heating all the rock around it. So you can get rock melting around the edges of your magma body. Also, you can get magma generated from mountain building events. So think of the Appalachians. When Africa finally, the last one hit North America, all that heat, that pressure, neither continent's given in, so you're going to get a lot of pressure and heat and strain that can form magma as well. So the temperature changes. Minerals will crystallize based on their melting points. The first to crystallize is olivine because it crystallizes at 1200 degrees Celsius. And I know I get this backwards, and I apologize if I'm confusing anybody. So the slides are correct. So olivine is going to crystallize. Oh, no, I said this right. Olivine is going to crystallize out. Those darker colored minerals are going to crystallize out and fall to the bottom of the magma chamber. Then you've got lighter colored silicates left. So this changes the composition of the magma. And this is called Bowen's reaction series. Right. This it says exactly the same thing, but probably easier to understand. So olivine crystallizes at the higher temperatures. Then as the magma starts to cool more and more, you get pyroxenes, you get feldspar at all these temperatures. Amphiboles, then micas, then the orthoclase, muscovite, and quartz. Quartz is the last to crystallize out at the coolest temperature. So this separation of the minerals is what turns basalt into granite. There is a NOVA program called Making North America. Kirkland, Jim Kirkland? No, not Jim Kirkland. Oh, he's a geologist, and he explains this process really well. Definitely. So that's on PBS. So if you have access to that and you're really interested, definitely look at it. He explains it a lot better, a little more simply. But also the magma can, because you've got some minerals crystallizing out as it cools, you can turn that magma into more of a granitic, and then that magma can become a secondary magma, and it might move to another volcanic area or crystallize somewhere else. And that's magmatic differentiation. Crystal settling, those heavier olivine minerals are denser than the magma, and they will fall down to the base of the magma body into the magma chamber. So the crystals will settle out as they crystallize out. So whatever's left, the magma that's left, will be a different mineral composition. And this just shows exactly that. As it cools, you're going to get the darker colored minerals on the outside, and then you'll get more lighter colored minerals on the inside. Or in this case, maybe the volcano will erupt and you'll get more granitic magma erupting. So this explains the difference between one volcano's composition and another volcano's composition. I mean, every volcano is going to be a little different. And as a magma body moves through the crust, it's going to heat it up and melt rock and incorporate that into the mantle. And that changes the composition as well. You might also get two magma bodies moving towards the surface at the same time. If they break through the rock together, they can mix and form a totally different composition. So again, diagrams like that. Partial melting. This is exactly what those previous slides were talking about. The magma, the minerals with the higher melting temperature crystallize first, and they will come out of the magma body and settle or form around the edge. So if you partially melt, that means that's crystallization. Either way, if it does the same thing whether you're crystallizing or melting, right? The temperature of the mineral is what's, the melting or crystallizing temperature is what's important. Okay, so if you start to melt an ultramafic rock, then that melt part, the liquid part, is more enriched in quartz, and that comes out of the magma. And if that crystallizes out, that moves out, and then you've got what's left is no quartz and more mafic. You can take that mafic rock, melt it some, then the next set of higher temperature minerals crystallizes and leaves, and then you get an intermediate. And same thing with granite. You can melt that intermediate. All the darker minerals, most of them are moved out. You've got mostly quartz and feldspars left. This happens, and this is a great diagram here. This happens deep underneath the crust, underneath the continental crust. So picture this is the Andes. The Andes Mountains are what's called a continental volcanic arc. You've got an ocean crust subducting down. When it gets to a specific or certain depth, it starts to partially melt. The melt is more buoyant than the solid rock around it, and it's going to float upwards like a lava lamp. And it's going to move through the crust and form volcanoes. So as that magma starts to cool, as it moves up towards the surface, all those higher temperature crystallizing and melting minerals will crystallize out first. So the olivine, on, and then the quartz will be left, and that's why we have granite bodies in the continental crust. Hopefully I explained that kind of well. Again, just another diagram trying to explain that better. So here's your original composition rock. Some of it gets melted, so this is the lower temperature, so you're just starting to heat it up. So at about 650 degrees Celsius, the lighter colored silicates, the feldspars and the quartz will melt and move away, and what you're left are unmelted dark colored olivine that needs more heat to melt. This is how a lot of the minerals you saw are found in areas like this, where we can see the different rock bodies that have separated out like this. Because you saw the mica was pretty big piece, you know, pretty long and a good diameter. This is how we find it. Yeah, basalt is the first type of magma to form under the crust. So most that erupts is called basalt. And then you get magmatic differentiation to form andesite and granite. So like I said before, we get some partial melting at the base of the crust, or also the lithosphere, the base of the lithosphere. And this part of the crust is called the asthenosphere, where it's super hot, but not quite enough to melt completely. But you get some partial melting of peridotite, and it's more buoyant. As it moves through the crust, it becomes more and more like granite, and all the darker minerals are crystallizing out and leaving that magma. Crystallized magma, igneous rocks, intrusive igneous rocks form different types of structures. So if you have a magma chamber that's just got the magma in it and it just cools and crystallizes there, that's called a pluton. Some plutons, maybe the magma has moved up and into cracks in sedimentary rocks and made a layer, and that's a tabular. Or you can have a massive or blob shaped. So here's some different ones. This is a fissure eruption. Iceland has eruptions like this. It's just a crack in the earth, in the crust, that unzips, and you get your eruption in a long sheet. These these structures here that move from the magma body to the surface that are long and thin, they're called dikes. And extensive large plutons that look like mountains after everything's eroded off are called batholiths. So everything's got a name just to identify and differentiate between the different structures. Dikes are kind of interesting. Then you can see them. They force their way through. Maybe they're parallel to the crust. Maybe they're perpendicular to the crust. Sills are again horizontal, comes up and fills in spaces and forms a layer. Forms columnar jointing. Come on, picture. Right, so here's a sill, and this is probably the Grand Canyon is what it looks like. So that has moved in here, and that was once connected over here. Then all this erosion occurred, and now we can see the sill. So we've got the jointing moving vertically up and down. If you've ever been to New York City and you're looking across the Hudson at New Jersey, there's a wall of black rock. It's a giant series of sills, and they form six-sided shape to it. So it looks like a long pillar, all connected, lots of pillars, and the top has a six-sided shape to it. Field trip. In a 13-person van, in a very small parking space, 12 of us, get out, look at the rock, get back in before we get hit, because it was just a one-lane road. Yes, that was an experience. So here's a volcano, probably out west somewhere, I would think. And the eruption, as you can see, left this volcano like that. But also, as the magma moved up and turned into lava, it erupted along this long line, and that's one large dike of igneous material. This is, I believe this is Iceland or Ireland, I'm not sure. The Giant's Causeway in Ireland is a series of these columnar six-sided dikes. So that's a good idea of how large they can be. Batholith, I'm not going to ask you to worry too much about what they are, but there's a good amount of them in Western North America. Phenolith, laccoliths. So that's about that. That's just in there to show you what these things can look like. All right, are we still awake?
Yes, ma'am.
Yes. Any questions at all? I think for the decompression melting, probably the easiest way to remember that, and I'm not going to ask you to get into, severe gory details. As the magma moves to the surface, the pressure is released and it melts because it's almost at the melting point. As it comes up, the pressure is released, then it can melt and flows out of the crust onto the ocean bed at a divergent boundary. Partial melting comes with plate subduction. When that plate gets to a certain depth, it starts to melt out the lighter colored silicates, the quartz, and that buoyantly flows up through the crust to the surface. Yay, I got a thumbs up. You can tell I don't deal with this on a daily basis, right? But again, those slides, those drawings of the decompression melting one and then the subduction for partial melting, that explains it or shows it pretty well. And I'm gonna, oh, well, we won't talk about volcanoes that much, I guess, but yeah, so think of the mid-ocean ridge, decompression, melting, and the formation of volcanoes at the Andes as partial melting. Okay? Yeah. Any questions at all? Probably not. No? Okay, well, we get through this stuff fast. If I'm going too fast, just tell me, okay?
Got it.
Got it? Okay. And I will put this on Canvas as soon as let me stop recording.